last time, what did we do last time? So we were doing all the dot product and cross product. So today what we want to do is just give some examples of how that that cross product thing works. So just give some, just sort of operate the equation. That's the first half. And then we'll talk about the other parts of the Bloch equation, the T2 and the T1 solutions. These are solutions to the equation. So you have the equation, the differential equation, and then solutions separately. We won't talk about how you got them. That will be on Wednesday. So today we just sort of look at how the solutions work. And this is important for understanding like how you get contrast between different tissue types. It's basically, it controls how the image looks. So, so we'll start off with just that first term of the Bloch equation. So the first term of the Bloch equation was that the change in the magnetic field over a short period of time, and that's the magnetic field in the tissue, is equal to whatever the current magnetic field is in that voxel, cross-producted with the B0 field, or the B field. And so the B field includes, like we said before, it includes everything. It includes the main magnetic field, the gradients, which have modified the Z component of the main magnetic field, and then also the RF, which is a very rapidly changing magnetic field. So that all that is in the B at any instant in time. So that's the first term of the Bloch equation. And remember the way that to understand which way the cross product goes, if you have a vector, so if you have a vector A over here and a vector B over here, how do you figure out which way the cross product goes? You move your fingers from the A to the B, and wherever your thumb points, which is supposed to be out, is the direction of the result of that multiplication. So that's the C. And what is the C? The C is that the change, the update in how you update the magnetic field. Now there was another equation that when we were doing all the dot products and cross products, which just referred to the length of this result here, of this C. So if you just look at the length of it, and that's what we're going to talk about today. So just the length of it, not the direction of it, but just the length of it. And so if we put those two things, that means get the length of the vector. And so the length of that update vector turned out to be equivalent to this simple equation, which was the length of the M vector times the length of that B vector multiplied. So when you multiply, this vector is a B, and when you multiply it by that gyromagnetic ratio, it just stretches it. That's what it means to multiply a vector by a number. So so the length of that guy times the sine of the angle. And what is the angle? The angle is this thing here, angle between the two vectors that you're multiplying. And so all we're going to do for the first half is just operate this equation just to see what it implies about the precession frequencies. So we'll start off with the starting case. So here's starting case. So our starting case, I can have four 4 examples. So it's about 1, 2, 3. So here we'll put the first one here. So there's make it a little shorter so I can lengthen it later. Okay, so that's our B field. Remember, we've rotated things sort of vertically, so that direction, the B field, the main B0 field is horizontal in the actual physical MRI magnet. Okay, and then here we've got our M vector. And so this guy is the B. That guy is the M. And then when we take the cross product, we get something that basically comes out. And then we paste it onto the end of the, right here, onto the end of the M vector to figure out how to change it, to change the M vector. And that one, that little guy there is the change in the M vector. And what does that imply? That implies that, and so then we get a new M vector. So here's our new M vector. And then if we keep doing that, what happens is we get this thing sort of precessing around like that, around in a circle. So there's make a little hole there for that guy to come out of the circle. So that's our basic, and the length, however long that dmdt is, tells you how fast it goes around. So that basically tells you how fast the precession frequency is. So that's our base case. Now let's sort of start fiddling with it. It's a very simple equation here. We're just going to fiddle with it just to see what it implies about, what this equation implies about precession frequencies when we change different parts of it. So that's the starting case. So now let's change the M length. So say we just have more magnetization. So that's our, so here, here's 1, here's 2, change the M length. So we'll leave the B the same. So here's the B, leave the B the same. But let's just say, let's double the M length. Don't change its angle, so we kept the angle the same. So here it is out to here, and then out to here. So we'll just double the M length. And then see what happens. So say we just have more magnetization. We did more RF, and we got a stronger local magnetization. What does that do? So here's the same B. So basically, so this is this is base case here, and here we double the length of the M vector. So what is that going to do if we just multiplied this guy by 2? Everything else held constant. It's just going to double. It's going to double the dmdt. And so here's that new precession circle that it's going to be going around. It's a bigger circle. And when we do that calculation, our dmdt is going to be twice as big. So dmdt doubles. So it doubles how much the vector moves for each piece of time. But now let's consider it's moving around a bigger circle. And so here's the old circle right here. And what is the circumference of that old circle? Well, that old circle has half the circumference, or the new circle has twice the circumference, because the circumference is just proportional to the radius of that circle, and that radius got doubled because you can easily see just from geometry that you just doubled the route around the circle. So what's the result? Same precession frequency, doesn't change it. So why did that not change it, even though we changed something? And the reason is because the m is on both sides, some form of the m is on both sides of the equation. So we doubled the m over here, it doubled the dm, but they sort of canceled each other out. So changing the length doesn't change, so how much local magnetization you have doesn't affect the precession frequency. We kind of already knew that because we said that the precession frequency was proportional to the b, and we didn't say anything, there's no m in there. Okay, so that was number 2. So slightly more complicated one. What we could do, what if we change the angle? So what happens if we change the angle? So like change this guy, leave everything else the same, but just change the angle. Now, how could we do that? You might leave the RF on for a little bit longer, so you get a different proportion of up versus down, and so you get a different amount of sort of z component of the magnetization of the m vector. Now you can actually make the m. It's possible to make the m vector, pointing in the minus z direction. So what happens if we do that? So if we make that drawing, so we take the same b, okay, so here's that same b, and then we'll take the same m, don't change the m. So here's where the m was before, and let's just change the angle of it. So make it the same length, but change the angle of it. So, instead of that angle, let's make a bigger angle. So what's going to happen now is we'll get a wider circle. But let's just sort of, look at this equation here just to see what's going on. So what's going to happen is the dm dt will be proportional to the sine of the angle, because if we make the angle bigger and then we take the sine of it, that's the factor that we'll have to multiply this dm dt by to figure out how big it's going to be. So what is, always just sort of, go back to, the high school trigonometry, like what is the sine? So, the sine looks like, it gets biggest at 90, and then at 180 it's 0, and then it's biggest negative at 270. So this is like 0 and 360, and this is 1 minus 1. So that's sine. So if we made the sine, say it was 45 degrees, and we made it, say, 90 degrees, it's going to move us from like over here, up there. And so it's going to make the dm dt bigger. But now we have to figure out the circumference of the circle that's going around. And if you just do simple trigonometry on that, what's going to happen is it's going to make the circle bigger by the sine. So same for circumference. So that means that it's going to be going around a circle that's sine of theta bigger, and the speed that it's going around that circle is also going to be sine of theta bigger, and so they'll cancel each other out. So what's the bottom line? Same precession frequency, nothing changed. So changing the angle doesn't change this precession frequency. So just whatever angle you start off with, you can change that angle as long as you don't mess with the length of the vector. Nothing changes. So that's kind of surprising. It seems like that ought to change something, but that doesn't. All these same things apply to a top. So just a mechanical top, the same things will happen to a top. Okay, so what does change the precession frequency? Well, we already knew that, and that is change the B. So change the length of B. So change the strength of the B field. And so in that case, forgot to label the B, so that's the B, there's the M. This guy is the dm dt. So let's just we'll double the B. So here's the first half, and there's the second half. So I made a bigger B. And we'll keep the same M that we had originally right here. So here's that original M compared to the starting case. And so now what's going to happen is here's the circle that it's going around. So it's basically going around the same size circle as it was before, because we didn't change, the angle. We kept the angle the same, and we kept the length of M the same. So M is still the same length, and B times 2. So if we go back to this equation, we just doubled the B, and so that's going to double the dm dt. And so now we'll double the dm dt. And so what does that mean? It means it's going to be going around twice as fast. So that's dm dt. So basically, so this is double the length of B, and that doubles dm dt. So that means 2 times precession frequency. And like I said, we kind of already knew this because we had that original equation, which was just our most simple equation, which was 2 pi times the frequency equals radians per second. So we could either have cycles per second, that's F, or radians per second. Those are like about 1/6 of a cycle. And that just equals that constant, that fixed constant, times the length of the B. So basically the B is the only thing that changes it, and we just sort of tediously went through the whole thing. But the reason to go through this is when you see an equation, you just have to, it's just a little machine, you have to operate the knobs until you really sort of see, what's going on with it. And so the bottom line is, if you change the length of the M, nothing happens. You change the angle with respect to the B, nothing happens. The only thing that affects it is if you change the B. Okay. So what are we doing? We're actually, we didn't say what we were doing is this thing here, that thing going around in the circle, that's the solution to this equation. So it's an important thing to keep in mind. So I didn't write it out. I didn't write out the solution. We'll do it later. So the solution, what the solution says is, for a given time, where is that arrow going to be? Because this thing doesn't have any given time in it. It just says, for a tiny bit of time into the future, this is what it's going to be, but it doesn't tell you what it's going to do, like for 5 minutes. So the solution will say, this is what the solution says, I can calculate whatever time you want, I'll tell you where the arrow will be. And that's actually what we've been doing here, just in words. We didn't actually write out the equations for it. So it's the solution. We've just been talking about the solution to this guy, to this differential equation. But you can see, you can reason with it pretty straightforwardly, just thinking about, the length of the vector and how long it takes to sort of go one cycle around. Okay, so any questions about this? So this was talking about the solution to the first term of the Bloch equation. The precession term. And if nothing else happens, like there's no friction or the m vector doesn't change, then it will just continue going around forever. And same with the top. If there was no friction on the top, just out in space, and it somehow had a perfectly frictionless point that it was stuck down to some surface with, the top would continue, just continue going around, wouldn't slow down. Okay, so that's the first term. So any other questions about? It's kind of concrete, sort of relatively straightforward. The only trick was just that the m, the reason things weren't changing is because the m was on both sides. In that second case. Okay, so now let's write up the whole rest of the Bloch equation. And the reason to focus on this again is that it pretty much explains why all the different parts of the image have the brightness that they do. And what you want to do in MRI, you might want to be looking for a tumor, or you might just want to try to see the difference between the gray and the white matter and have some contrast difference between the gray and the white matter. And so the second part, the second and third part of the Bloch equations are one of the main things that describe how bright the different parts of the image are going to be. So here's that first term again. So that was whatever the m field, the m vector was, cross-producted with this, whatever the b vector was. We already did that. That's the term 1. And then the second term, there's different ways of writing this out, and if you look in different textbooks, you'll see slightly different ways of writing it out. But one way of writing it out is to sort of fish out the XYZ components of the m. And that's what this means. It's not a bold m, doesn't have an arrow on top of it, so it's just the x component, the x coordinate of the m vector. And then times the I vector, and the I vector is a way of writing a vector of length 1. So it doesn't have any, it just has like a standardized length, and we can turn, so this whole thing together will essentially be a vector that is the x component of the total m vector. And so before we go any further, let's just write that out here. So here's our coordinate system, and we have some m vector. So say here's an m vector slightly coming out at you. And so if we divide that vector into its into its components, we've got, here's the, oh, and then we have to sort of establish our coordinate system. So there's the z-axis, and here's the y-axis here, not the x, and here's the x. Now, when you look at that, you're like, why is the x coming out? Isn't the x sort of go off to the right? That turns, if we go back to, remember our original picture of the magnet, look like this, and our coordinate system there was, the z was coming out that way, remember? And then, you know, the x was coming out at you, that was the left and the right, and the y was going up. Now that's sort of strangely different, but convince yourself that this is the same coordinate system. So if you see, like, if you take this coordinate system and basically just like rotate it about a third of a cycle, you'll end up with the z up and the x sticking out at you. So these are these are the same coordinate system. And so we'll make a lot of drawings like this with the x sticking out at you and the y going off to the right. But it's the same one that we had before, which was the z sticking out of the bore and the y going up and the x going left-right. So going back to our picture here, so here's those three x, y, z coordinates, and so what does that mean? So that means like the mx. So where's the mx? So here's the mx. So that's mx. So that's a length. That's not a vector. That's just a number. And then what is that thing after we multiplied it by a vector? Well, we would have our vector of unit 1. So there's our I vector. So that's a vector pointing in the x direction, length 1. And then we multiplied it by mx. And so then we end up with a vector that's going all the way to the end of mx. So it's just sort of going very slow, but just to make sure everybody's on the same page. So this guy's just a number. That guy is a vector of length 1. You multiply that, you get a vector that is, this vector going from the origin to the point on the x-axis that corresponds to the x component of the m vector. So we're just dividing the m vector up. So we're just dividing the m vector up into 3 vectors. And so this is just the x1. And then we've got the same thing for the y1. So here's a j, meaning sort of like a vector that goes 1 along the y-axis. And then you divide that by t2, which is a time constant. So this guy is a time constant. So why is that guy in the denominator? So let's think about that. So this whole thing is a decay term. So why is it decaying? Well, it's because it's being subtracted off. So it's being subtracted off the x and the y component. In our to arrive at our final dm dt change in the m vector. So the reason that you put time constants in the denominator is because, say we turn up the time constant. So like make the time constant twice as big. This is why you just have to operate the equation. So if we double the time constant, so make it from, say, 50 milliseconds to 100 milliseconds, that's going to be dividing by a bigger number. if you divide by a bigger number, this thing is smaller, and so less gets subtracted off. So that's why the time constants always appear. So a longer time constant means less is subtracted off, which means it lasts longer. So that's our time constant. Okay, so almost done. And so then we have one more minus for the third term. And this one has to do with the z component. And so the z component but it's got yet one more new symbol in it. So that's the z component, just the length of the z component, not a vector. And then minus this thing, mz0. And that's a new thing. That guy's a constant. And that whole thing is multiplied by the k vector, k unit vector, which is a vector of length 1 going in the z direction, divided by t1. Okay, so what are these things? So this is another time constant. This guy's another time constant. This guy is the mz, so that would be, here's the mz. mz right there. And then finally, what's this thing? So this thing is another constant, and this one is called, so it's a constant, not a variable. This guy's a variable because that mz can change over time. And why does it change over time? Well, that's what this whole equation does. You get all this stuff together, and then it says this is how we're going to change the mz, my, and mx. So that this dm dt will change mx, my, and mz. Okay, so this guy's a constant, and let's put it down. I'll put it down here so I won't get in the way of other stuff. So that guy is a constant, what's the equation for that constant? So the equation for that constant, that one's called the equilibrium magnetization. So let's put that up there, a constant. It's called the equilibrium magnetization. And so you can sort of imagine it's the magnetization at equilibrium, whatever that is. And so what does that mean? It just means if you stick something in the magnet, how magnetized does it get? So how big of an M do you get from just sticking something into the magnet? So the magnet is a big B, 3 Tesla B, and you stick a body in there, and then you just say, how well did the body get magnetized? And what does the equilibrium mean? It means you stuck it in there long enough so that it got magnetized, however much magnetized it was going to get, and that was it. And that takes a while. It takes about 2 seconds. So it actually, when you stick yourself into the magnet, it takes a full 2 seconds before you get magnetized. You're not magnetized very well. Couldn't even pick up a paper clip, but just very, very slightly magnetized. It takes about 2 seconds. And so what controls that? So the equation for that, it's got a lot of things in it, so this is like what's the length, of the magnetization vector in a sample after you've stuck it in this field for a long time, like 10 seconds. And it turns out it's pretty much strictly to do with the number of protons in the sample. It's again like this equation has a lot of numbers in it, but all of them are constant. So it's got the gyromagnetic ratio squared, and it's got Planck's constant squared, and then it's got the B0 field and the number of spins, number of proton spins. Those are the only non-constant things in there. And then on the denominator, there's Boltzmann constant, and then there's the temperature of the sample. So let's annotate all those things. So this is gyro. This guy, H, is Planck's constant. You know, that's something you have in quantum mechanics. B0 is just the strength of, you know, the B0 field. NS is just the number of spins. Num proton spins. So it's just literally just the total number of hydrogens. So it doesn't, amazingly, it doesn't matter what the stuff is made out of. It's just count up the number of hydrogens in it, and that's why quantum mechanics is so simple. So you can just ignore everything about like the sample. It could be like a piece of dead meat, piece of, you know, live meat, like a good subject, or, you know, a rock. Doesn't matter. Just how many protons does it have in it, and that's going to tell you for a given B field what the equilibrium magnetization of that thing is. So this is, you know, Boltzmann constant. So that all those guys are Planck's constant, gyro constant, gyromagnetic ratio constant, and the temperature. So that's just the, you know, apps temp sample. So obviously, if you're scanning living things, that's pretty much going to be the same all the time. It's, body temperatures, assuming they're not dead. So that's another variable, but it's one that's, you know, for living samples isn't a problem. So basically, these are the only non-constant. So it's just the number of spins. And so that thing, so this thing, you know, goes up here. That's where we get that. So now let's just look at how this, again, we have to just like operate this equation here. So what this says is the mz component, what's the biggest the mz component can get to? The biggest it can get to is mz0. So because that's the equilibrium magnetization, that's the most you can be magnetized when you just get stuck in the magnet. And so after you've been in there a long time, what happens to this term? Well, mz is going to be the same as mz0, and you subtract that off, and you get 0, and so this term is not going to do anything. And that's good, because that's sort of, now we're at equilibrium. It's not changing the magnetization, the z component of the magnetization. And then there's another time constant down here, and so this one is, it's called a decay term, but it's actually a regrowth. So sometimes you call it, you know, decay, but what does it do? It's regrowth. So it's got a minus in it here, but it's got another minus in it here. So let's just take a simple example. Say you aren't to equilibrium yet. You stuck yourself in the magnet. It's only been like 1 second, and so you haven't gotten completely magnetized, and so mz is going to be less than the equilibrium z magnetization. So this number might be, you know, if that one was 1 and this one was 0.5, then this thing is going to be minus 0.5, and then we minus it, which minuses the minuses, that makes it a plus. So this whole, the effect of this whole thing will be positive until you reach equilibrium magnetization, and then it will be 0. So that's why it's a regrowth rather than a decay. They call it a decay, T2 T1 decay, but it's really sort of T1 regrowth, and the reason is just because of the way the signs are set there. Okay, so all good so far. So that's the whole Bloch equation. That pretty much, like I said, it's like there's only 2 equations for a transform of the Bloch equation. We haven't really sort of fully worked through it, especially if you do some wiggling fields. It's going to be more complicated, but basically that describes how bright the different parts of the image are going to be, depending on these constants, and these constants differ for different types of tissue. So, like, you know, blood will have a certain T2 constant, gray matter will have a certain T2 constant, white matter, and they can separately have different T1 constants also. Okay, so now let's do the solutions to these two guys. So these two guys, again, it's a differential equation, so it just says how things are going to change a tiny bit into the future. And so we're not going to say how we got the solutions. We'll do that next time. We'll just say this is the solution. And so let's start off with T2 decay. So what is the solution to this thing? And one thing you might wonder is, like, how can we just solve for one of these guys and ignore the other ones? Well, the trick here is that they're all perpendicular to each other. So the T1 is going to be related to the z component. The T2 is going to be related to the xy component, and the precession is going to be rotating around in the xy plane. And so basically, because they're effectively all perpendicular to each other, I didn't explain why this guy is going to be perpendicular to the precession, but we will two lectures from now. They're basically all perpendicular to each other, and so because they're all perpendicular to each other, these effects, you can ignore some of the other ones and just pay attention to one, because if you change one of these guys, it won't affect the other term. And so that's how we can sort of just do a solution for just a piece of the equation instead of the whole thing, although in the end we want the whole thing. Okay, so what is the solution? So the solution is the mxy component. So now we can change the notation again. So you'll see this a lot of times if you look in books. And what is that? That's just if we add the x and the y component together, that would be right there. That's adding the x and the y component together. And then if we look at, like, what is the length of that guy? So that guy is, mxy, but we could also just look at the length of that. So that's what the mxy vector is. So it's just the length of the x and y component of the m vector. There's m vector right there that has the z component. Get rid of the z component, you just get the mxy. So that's the length of that guy. So it's not a, we could either think of it as a vector going out there, or we could just think of it as what's the length of that vector, which is not a vector, that's just a number. So that's what we're writing here. But this is a solution now, and so now it's going to be a function of time, so that we can figure out, like, what is the answer for any arbitrary time, as opposed to just predicting a tiny fraction of time into the future. So what is that equal to? Well, that is equal to yet another new symbol, which is, this is the way it's usually written. That's just a single thing. It's a single number. So this, that guy is this is basically the, m, x, y at start. So this guy, it isn't in this equation up here. This one's called an initial condition, and we'll show where it comes from next time. That guy's an initial condition. So that's just a number. This is just a number, scalar. So that's a single number for the, what is the length of the magnetization that you, of the xy component of the magnetization that you started out with. And like I said, it isn't in this equation, and where do we get it from? That's for next time. So that's the first part of the T2 decay equation, and then that's multiplied, and that's just a regular old multiply. It's not a dot product. It's just a regular old multiply times e to the minus t over t2. Okay, so that's our solution. That's our solution to the T2 decay part. So this is solution to that guy. So now, yet another symbol. So we've got e to the minus t over t2. What does that mean? So, well, we got a time constant, and it's in the denominator, minus t over t2. So when you see that, whenever you see something to a minus power, let's just think about how this works. So say we set t to 0, like time t equals 0. What is the value of this thing going to be? So anything to the 0 power is 1. So anything to the 0 power is 1. So you can start at 1. Whenever you see e to the minus something, e to the minus variable, not squared, e to the minus, just minus variable, not squared, what you should think of something that that looks like this. So it starts at 1, and it falls off like that. And just so you can go and plot that in MATLAB. In MATLAB, it will be exp something. So you could do, exp of 0 and just, see what that is. Or you could just plot out exp for, a whole bunch of values of, of x, and you'll see it will fall off like that. So as you go to a very tiny number, you'll get something slightly less than 1. And then as the number gets bigger and bigger, because it's a minus in the exponent, you'll get smaller and smaller and smaller. So whenever you see e to the minus variable, this is what you think of. So it starts at 1, but it doesn't start at 1 because it's multiplied by this guy. So basically it starts at whatever this guy was. So this is whatever the magnetization in the xy component was, 0 plus, which means right after the pulse. So, start. So, 0 plus means, right after pulse. So after we did a little pulse and caused some magnetization to appear, and then we turned it off, and then we said, this is our starting point. So right after RF. So we turned on the radio transmitter for just a little burst and then turned it off. So that's what that 0 plus means. It means right after the pulse. 0 minus would mean right before the pulse, but 0 plus is just right after the pulse. So that's our starting point, and it just falls off. And so what is our goal? Well, our goal is to say, well, what if we have something with a different T2? So say this guy was a long T2. What if we had a shorter T2? What would that look like? Well, so a shorter T2 would be a smaller number here in the denominator, but what that's going to have the effect of is causing a more rapid fall off. And again, just go into MATLAB and just, put, t over n and then fiddle with n and just see what that does to the equation. And so if you just work it through, it's very simple algebra, but if you put a bigger number in for T2, what's going to happen is it will fall off less rapidly. If you put a smaller number in for T2, it's going to fall off more rapidly. So this is what the curve would look like. Now, notice they start from the same point, and they end up at the same point after a long time. And really, what all the action is just what happened in the interim. So here's a shorter T2. And then, don't forget, this is time going in that direction. Make sure we label the axes. And then this is the amount of mxy going in that direction. So what is MRI all about? It's all about at what point should we try to collect some data? At what point in time should we try to collect some data so that we get like a lot of contrast between these two different tissue types? So if you collect data after a long time, there's going to be no signal. If you collect it right at the very beginning, there's going to be no contrast. But in this little in-between region, that's a good place to try to see a difference between two different tissues. So that's the T2 decay, and then T1 decay is a little more complicated. T1, quote unquote decay, because it's actually regrowth. So what's the equation for T1 decay? So that one can also be written in slightly different ways, but it's and all I've done here is just plotted. I just plotted that equation. Just plot. So how do we get the z component? The z component is that mz0 business, and the solution here is 1 minus e to the minus t over t1. That's a 1, not a 2. And plus another one of these funny 0 plus things, like how much z magnetization did you start with? And that one's also multiplied by that minus t over t1. And you can see this this equation, sometimes they'll multiply it out, and so you have like mz0 plus, you might see it in this form, mz0 plus minus mz0. That's the same thing. And then that whole thing times e to the minus t over t1. So those are just algebraically the same. Some textbooks will have that other one in there. And so what happens, when we plot this guy? So when we plot this guy, I'll try to keep the z-axis about the same, the x-axis, the time axis about the same. So this one is much longer. So because we said, this, what is the time here? The time here might be, say, 50 milliseconds. So it's pretty short. So in this case, it's going to be quite a long time because I could take seconds. And we might be able to start at a negative mz. So it turns out you can, it's possible for mz to be negative. It's not possible for mxy to be negative. So mz can be negative. And so what does this look like? Well, it just recovers quite a bit more slowly, and it keeps going up. And what is it aiming for? It's aiming for something that is mz0, because after a long period of time, so this is time, and this might be, say, 1 second. Aren't quite there yet. Like that. And so we have the same thing here. So what if we have a T1 that's a little shorter? So if a T1 is shorter, it's a smaller number here. And what's that going to do? That's going to cause the regrowth to happen quicker. So we'll start at the same thing. This is that mz right after we turned off the RF pulse. So what will happen is they'll start sort of almost on top of each other, and then slowly over time this guy's recovering a little quicker. And so this guy will be, slightly recovering a little quicker, but, because of this equation down here, they eventually end up, both down the line, they'll just end up exactly at mz0. And so we have the same thing going on here. We want to figure out, what is a good time to record, about 0.7 seconds. where there's a big difference between these. Or this is a particularly good point to record because this guy has 0 and this guy has a bigger number. So that's sometimes we try to do something like that where we set up to get one tissue has 0 longitudinal signal and the other one has a bigger signal. So that's basically, now that's all of MRI, all of the basic contrast part of MRI. So you get this very quick decay of the XY component, and then you get a much longer time to regrow the Z component. So if we drew that out, what does that look like? It's the last thing, just one more minute. So let's just draw that out in 3D. So say we start off with our M vector here. And it's precessing very rapidly. So it's precessing rapidly, like 123 million times a second around the XY axis. So here's the Z component, here's the X coming out at you and Y over here. So what happens? Well, it very rapidly goes in and gets rid of all the XY component. And then it slowly grows. That takes like seconds until it finally gets up to MZ0. So that's fundamentally what the MRI signal looks like. You hammer it with an RF, you make a very large XY signal, and then that quickly decays away to almost nothing, and then it slowly wiggles its way back up until you get, after a long time, after like a couple seconds, you get back up to MZ0, which is just the number of protons, number of spins. Okay, so that was all of the Bloch equation solution. So we'll go over, like, how do you get these things? Where do these things come from? But this is sort of the full Bloch equation, and it pretty much describes how all the different brightnesses of the images are going to be, and all the different pulse sequences, all the different ways you can run the scanner. Okay, so that wasn't quite as bad as last time, hopefully. So we'll see you guys on Wednesday.